Today we want to test whether the antenna actually works well under real-world conditions. This episode is about testing our self-made 70 centimeters loop antenna in the ham radio band in a real radio field. For this purpose, we connect the antenna to an SDR receiver, which allows us to record a number of samples of the received field strengths over a period of time. Then we can make statistical evaluations and objective comparisons. The method can be used in general to assess a radio channel. That's why I explained the method in more detail in this video. So, how do we judge the performance of our homemade antenna? Of course, it would be nice to be able to measure the absolute received power and the antenna gain precisely. However, you need a lot of professional equipment that is extremely expensive, and it also requires a lot of know-how and experience to perform this kind of measurements. But there is a clever method using relatively simple means to assess the performance of an antenna very well. And in addition, this method is very close to real-life scenarios. We can make a comparison with an antenna of which we know its characteristics. I'm using a quarter wavelength monopole for this purpose. Since radio signals are always volatile, we have to take a number of measurements and then evaluate them statistically. For this purpose, we use the software-defined radio receiver RSP1A and the software SDR Uno. This combination works really great. It outperforms solutions with simple USB sticks by far. Before we carry out a long-term measurement, let's just take a look at what's up on the 70 centimeters ham radio band. First, we use the quarter wavelength monopole. Well, we see some activities on the band. There is some dynamic and some static carriers that the SDR receiver is picking up. Now let's look at the same frequency range with our new loop antenna. We can now see more activities. And in addition, the reception levels are now higher than before. That's very interesting. It is already an indication that the loop antenna is producing a stronger receiver signal. Of course, this is only a qualitative comparison so far. We go on with quantitative measurements now. In order to get a really objective comparison, we have to carry out long-term measurements and later compare them statistically. To do this, we look for a signal that remains constant over a long period of time. I found some kind of radio beacon here at 432.058 MHz that has been sending a constant signal for a few hours. We use it to record the received signal strengths in dBm for both antennas within a period of 2 hours. A sample is taken every second, which is then saved into a file. The yellow lines at the bottom of the video indicate this in our waterfall graphic. It is really an interesting feature that we can use very well for our purpose. Let's take a quick look at the file that we obtained. I recorded the data for the different antennas in 2 different CSV files. Since these are text files, let's just open one of them with a standard text editor to see how they are structured. In the first column we have a date and a timestamp. The second column shows the receiver frequency. The third column shows the received power in dBm, which we will use for our statistics. The fourth column even gives us the signal-to-noise ratio in dB, which we do not use this time. With Excel, as well as with other spreadsheet tools, you can import CSV files. I've shown how to do it in earlier videos. It's very straightforward. By the way, CSV stands for comma-separated values. The format is kind of standard and is often used by devices or apps to record and exchange data. Dear SDR Uno developers, very well done, thanks. Depending on which Excel country settings you use, you may have to replace the dots with commas in the dBm values. You can easily do this with Excel's Find and Replace function. Doing this action manually would be a bit time-consuming with more than 7,000 rows. Now we can create the statistics we need with a few standard functions. We can determine the minimum and the maximum, then the standard deviation. The mean and the median value are interesting. Strictly speaking, the median value should always be considered here, since the transformation of the power values onto a dBm scale distorts the mean value. As a result of this, the dBm mean value actually has no physical meaning. So better take the median value for this kind of evaluations. Physically, it simply means that 50% of the values are larger and 50% are smaller than the median value. The median value always remains the same, regardless of whether the values are presented as a power value, a voltage value, or logarithmically normalized in dBm. If we want to graphically represent the distribution density of the received power, then we have to divide the values into categories. I simply use Excel's rounding function for this. This gives me the values in categories of 1 dBm steps. Now I only need to count the number of values in each category to get the so-called distribution density. I do this with a pivot table. I define the categories as rows here, and then I determine the number in each category here. And then we have the distribution density, which we can of course also show graphically here. Let's summarize the results of our measurement campaign now. When comparing the distribution densities of the received power, you can see immediately that the loop antenna has a clear advantage. On average, it brings around 5 dB more power to our receiver front end. That's quite a lot, and it confirms the behavior that we have already seen in our tests at 866 MHz with a LoRa radio link. However, in contrast to LoRa, the standard deviation is similar for both antennas. We need to talk about this for a moment. We measured here with a very narrow band carrier, while a LoRa signal has a rather wide bandwidth of 200 kHz due to its modulation. Furthermore, the 432 MHz radio beacon transmits from an exposed site. We have a quasi line of sight scenario, so to speak, and as a result a stable and dominant direct signal compared to the reflections that we also receive. In the case of LoRa, we had a rather diffuse radio field consisting just out of reflections. I think that makes the difference in the standard deviation. Overall, we once again have a very interesting result. What do you think about it? Would you use such a loop antenna? Write me in the comments. If you want to follow the comments, just subscribe to the channel. The insights and the summary. The loop antenna is larger than a quarter wavelength monopole. However, it takes up significantly less space than, for example, a ground plane antenna, whose stubs naturally protrude into the room, while the loop antenna remains in one plane. The approximately 5 dB stronger received signal speaks for the loop antenna, because it means almost twice the range and a higher security of the radio connection. As said, there are a number of ways to implement the antenna. Maybe this antenna principle is of commercial interest for you? In that case, please let me know. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.